Hi everyone. So in this session we are going to discuss about mathematical analysis of non-recursive algorithms. So in previous sessions we learned about algorithm analysis and asymptotic notation. In this topic we will study a asymptotic method for mathematically analyzing non-recursive algorithms. We will also understand this process through practical examples. So before analyzing any algorithm, we should understand the main components of the analysis framework. These include measuring the input size, choosing the unit for measuring running time, determining the order of growth, analyzing the algorithm in the best case, worst case and average case. So these steps helps us estimate how efficiently an algorithm. So this is the general plan for analysis. The mathematical analysis of non-recursive algorithm follows a standard procedure. First, determine the input size, usually represented by n. Next, identify the basic operation which is normally located inside the innermost loop and consumes the most execution time. Finally, determine whether the number of execution depends only on the input size or also on the input values. If the input values affect execution, we perform separate best case, average case and worst case analysis. So general plan for analysis. After identifying the basic operation, we write a mathematical summation representing how many times it executes. Finally, we simplify the summation using standard mathematical formulas. From the simplified expression, we identify the algorithm efficiency class such as big O of n, big O of n square and big O of log n. To simply execution counts, we use the standard summation formulas. For example, the sum of the first n natural number is n multiplied by n plus 1 divided by 2. Similarly, the sum of squares of the first n natural number is n multiplied by n plus 1 divided 1 multiplied by 2 plus 1 divided by 6. So these formulas make complexity analysis much easier. Finding the largest element. Let's consider our first example. This algorithm finds the largest element in the array. It starts by assuming the first element is the largest. Then it compares every remaining element with the current maximum. Whenever a larger value is found, the maximum is updated. So finally the algorithm returns the largest value in the array. Let's see the analysis of this algorithm. The input size is the number of elements in the array represented by n. The basic operation is comparison. So a of I greater than max value. Since the every size of n performs exactly the same number of comparison, there is no need to analyze separate best, worst, average cases. So counting comparisons. So the comparison is executed once during every iteration of the loop. The loop runs from 1 to n minus 1. Therefore, the total number of comparison is represented by the summation from I equals 1 to n minus 1 of 1. So solving the summation, using the summation formula, the total number of comparison becomes n minus 1. Therefore, the running time grows linearly with the input size. Hence, the efficiency class of this algorithm is big O of n. So, element uniqueness problem. In this problem, we determine whether all the elements in an array are distinct. The algorithm compares every element with all the remaining elements. If any two elements are equal, it immediately returns false. Otherwise, after checking every pair, it returns true. Analysis. The input size is again the number of elements. The basic operation is equality comparison. inside the inner loop. The basic operation is the equality comparison inside the inner loop. Unlike the previous example, the number of comparisons depends not only on the input size but also on where dual elements appear. So therefore we need best case, worst case, average case analysis. So in the best case, the first two elements are identical. Only one comparison is needed. In the worst case, there are no duplicate elements or duplicates appear only at the end of the array. In practical analysis, we usually focus on the worst case because it provides maximum running time. To calculate the worst case running time, we count every comparison inside the nested loops. The mathematical expression is written as a double summation. The summation represents all the comparison between different pairs of elements. So after simplifying the summation, the total number of comparison becomes n multiplied by n minus 1 divided by 2. Ignoring constant, the running time grows proportional to n square. Therefore, the worst case time complexity is big O of n square. Now consider the matrix multiplication algorithm. Three nested loops are used. The outer loop selects row, the middle loop selects column, and the inner loop performs multiplication and addition. The result is stored in the output matrix. Analysis of matrix multiplication. The input size is matrix order n. The basic operations are multiplication and addition inside the innermost loop. Since all three loops execute n times, the number of basic operations depends only on so each loop runs n times, therefore the multiplication operation executes n into n into n, which equals n cube times. Hence the time complexity of the uh, standard matrix multiplication is n cube. So this binary representation, this algorithm uh, calculates the number of bits required to represent a positive decimal number in a binary. The variable count starts at 1. During each iteration, the number is divided by 2 until it becomes 1. Finally, the algorithm returns the total number of binary digits. Analysis. The input size is measured using the number of bits. The basic operation is comparison and n greater than 1, since the value of n is divided by 2 during each iteration. The number of iteration depends only on the size of n. Each iteration reduces the value of n by half. Therefore, the number of iteration is approximately log base 2 of n. Hence, the efficiency class of this algorithm is big O of n, which is highly efficient for large inputs. So let's summarize today's discussion. We learned the first 5-step process for mathematically analyzing non-recursive algorithm. We identified input size, selected the basic operation, wrote summation expression, simplified them using mathematical formulas, and determined the efficiency class. These are the